Day class. So this is the recorded version from the lecture that I did to you last few weeks before the Holy Week. Um, this is Dynamics of Rigid Bodies, MB266, and specifically this is lecture 3 for Kinetics and Force Acceleration. I'll be running again the basic concepts here for force and acceleration, a bit of review of what concepts are important from lectures 1 and 2, and of course we're going to go over some sample problems again, those that I already showed to you guys in class, and the ones I skipped or fast track. So this will be both a lecture and a problem walkthrough, but more on problem walkthrough. You know the reference I'm using. Feel free to feel free to skim over those lessons and read over those sample problems in the book. Okay, so let's start. Essentially, we're gonna be talking about kinetics. I said, let's go about the definitions. What's different about kinematics? We're gonna talk about equations of motion. How do we set now? How do we combine the concepts of free body diagram and identification of forces, and then combine it with the kinematic equations that we know. Of course, we got to recap about what friction force is all about and spring force. And my favorite, we're going to be talking about normal and tangential coordinates. So we're going to be recapping about normal and tangential acceleration. And second law of motion mentions that if you have acceleration accompanied by mass, you generate a force, basically. Okay, so what you'll need here, okay, a basic understanding of your differential and integral calculus like we did before. And of course, that's pretty redundant, understanding of our previous lectures. Just like with statics of rigid bodies, free body diagram is back in the game. And then finally, and for you to get all the concepts here, you need to practice so that it becomes quite intuitive to you guys. So this is the recap of the formulas that we use back then. You don't have to remember all of it. You just have to remember a few and the most commonly ones. And if you can't, if you forgot the formulas, you can always derive them using three basic equations listed below, and just using calculus. And of course, we also have this one, the magnitudes of normal acceleration and tangential acceleration. Just recall that for tangential acceleration is simply the first derivative of velocity with respect to position here, ds. And of course, normal tangential would be normal acceleration will be the square of the velocity divided by the radius of curvature represented by the symbol rho. Okay. Some definitions. As you know, dynamics is basically the understanding of motion, acceleration, and forces acting upon them, and how we understand these three basic variables on analysis of objects and systems. It's divided into two. There's kinematics and there's kinetics. Kinematics, we primarily concern ourselves with the geometric properties of motion. How fast it is, how far from the original position. Is it accelerating? Is it decelerating? So those are the kinematics questions. And for kinetics, we deal with what causes the motion. So we deal with the forces that causes the motion. And with forces that causes motion, we have to recall that the foundation, Newton's three laws of motion. So we have the first law, second law, and third law. Or first law pertains to inertia, particle at rest, and moving along a straight line at or constant speed. Velocity tends to remain at the same state provided not subjected by any unbalanced force. And of course, by second law here, we have the famous formula force equals the mass times acceleration, where particle acted upon by an unbalanced force F. Experienced acceleration has the same direction as the force and a magnitude, directional proportion to the force, as shown here. And of course, we have the third law. We have the mutual forces of actions and reaction between two particles are equal and opposite and collinear. We'll be discussing and applying the third law more on our next lessons, more on impulse and momentum and work and energy, so to speak. Okay, and just to recap, we have now next is the friction forces. Okay, there we go. So frictional forces refers to the force that oppose the relative motion or tendency of motion between two surfaces. Okay, it's basically the resistance of one surface to the other. The higher your coefficient of friction, your mu here, the more resistant your body is to movement. So you'll become static. Okay, and we have two kinds of forces, frictional forces. We have the kinetic friction forces and static friction forces, okay? And that means that we have two different kinds of coefficient of friction. We have static coefficient of friction and kinetic friction, okay? Hopefully I changed this one. Okay, so the basic formula here is f of s equals to mu times the normal force. Okay. As for the next one, we have the kinetic friction. It's pretty much the same formula. It's just that kinetic friction here is always less than the static friction because it's moving, so that the resistance is not enough for it to be static. So there's movement here that becomes a, and most of the time we'll be going to be using a coefficient of kinetic friction, both of which will be provided in the problems or during tests or quizzes. Okay, and normally that the kinetic friction is about 75% of that of static friction. Okay, and then of course we have our spring forces, cables. So just a quick recall. So again, there are forces exerted by spring, like it's stretch or compress. Cables here transfers the weight, basically. When in contact with a smooth surface, we have what we call, normal force. It's basically exists perpendicular to the surface. For spring, the formula here is FKS, where K is the spring constant or stiffness. S here is the elongation, basically. So it's positive when your final position is greater than of your initial position, and it's negative if a core compressed when your final position is less than that of your initial position. Okay. So for our cables here, we assume first that this cannot be stretched and their weight is negligible for now, but we're just going to add the element of friction here in between the pulleys. Yeah. All right, for our first problem, I know we've already discussed this. For the sake of people who haven't seen the lecture or wasn't able to attend the class, I'll just gotta talk about this. So the first one here is the 50 kilogram crate. Shows stress on a horizontal surface for which the coefficient of kinetic friction is 0.3. If the crate is subjected to a 400 Newton towing force is shown at an angle of 30 degrees, determine the velocity of the crate in 3 seconds starting from rest. Now, the question here up to before the determine the velocity, it's pretty much a static static of rigid bodies problem, but we now add the element of kinematics here. So there is, we now add the element of dynamics here. So determine the velocity of the crate in 3 seconds starting from rest. So the way you do here first is, identify your given. So far you have your 50 kilogram, here's the mass. You can list them down later. Okay, or you can list them down now. You have your coefficient of kinetic friction of 0.3. It starts from rest, so you know very well, and it's reiterated here, starting from rest, that it has an initial velocity of 0. That has a towing force of 400 newtons at an angle. So it has its x and y values here, in this case, yeah. And then what else do we know? Okay, that's pretty much it. So the first thing we gotta do here, of course, is draw our FBD, so our free body diagram. That's the first things we gotta do here, aside from writing down your given. But that's just for me to calm my nerves when I'm trying to solve problems, so that I know what do I currently have and what to do next. And then from there, I just draw my free body diagram. You know the rules. So we simplify we simplify the drawing. So here we draw the crate. The weight here is pointing downward, which is basically mass times acceleration to the gravity. And then we have the perpendicular force. And then we also have the frictional force represented by F, or F sub S if you want. Since it's kinetic, I always most likely got to do F sub K, so that's proper distinction. Then, of course, you apply the force of 400 newtons. And from there, we can set up our equations of motion. Okay? Okay. So as for the solution, yeah, So we start first with, there we go. So we're gonna go with horizontal and the vertical directions. So we start with the horizontal here, or in this case indicated by x. So we have the summation of all the x forces is equals to mass times the acceleration sub x. In this case, we know mass, but we don't know a sub x. But for forces under the x-axis, we have 400 cosine 30 degrees, and we have the frictional force. So we can just substitute that here, and that will be our equation 1. And then next up is, we don't know the perpendicular force, and we don't know the acceleration here. So we need another equation to solve it. So luckily, we have the y forces. So summation of forces on the y-axis is equals to mass times a sub y. In this case, do we have a acceleration on the vertical axis? No, it's only moved. The short answer there is no, because it's only moving on the horizontal plane. It's not levitating, it's not moving up, it's not projectile. So it's basically 0 here. And y forces, we have 2. We have the weight and the perpendicular force. Actually, we have 3. We have the weight, we have the perpendicular force, and then, of course, the y component of 400 newtons. So we just sum it up here, and we have this. And luckily, it's going to be equal to 0, so we're going to be able to solve the perpendicular normal force here. And yeah, so we're going to be solved for NC using equation 2, and here is about 290.33 newtons, which we can then substitute in equation 1 to solve for our acceleration. And our acceleration is around 5.186 meters per second squared. And from there, we can now use this to solve our final velocity at time equals 3 seconds. So using our kinematic formula, I think the best formula there will be Vf equals to Vi plus At. There we go. And we simply substitute our known variables here, and we will have the answer of 15.5587 meters per second, or simply put, 15.56 meters per second. Okay, that's easy.